Welcome back to the video lecture series for Introduction to Data Programming using Scala. We've been looking at parsers for context-free grammars, and we saw in the last video how it would parse to a specific default format, which technically is enough for us to traverse through and look at basically what's called the parse tree. However, a lot of times you don't want that output, and so now we want to look at how we can specify our own output for parsers. In this case, I'm going to go ahead, copy, paste, and I'm going to make slightly different versions of all of these. And I want to make a parser that doesn't return any, it returns a double. Because after all, that is what we want this to give us back. Okay, so how do we specify the output of these things so that it's not the default? And the answer is the parsers have an operator called caret caret. So just to make it clear, oops. Let's see, I need this to be a function. So after the caret, we put a function that takes the output, the normal output of the parser, and it is supposed to return to us some alternate format. So in the case of this, I guess we can say x goes to 5, x goes to 5. It's going to be unhappy with our choice of I'm trying to do this too easily, and it's not liking parameter. A lot of times you use partial functions here, but I feel like I should be able to get her. Okay, that's the. I wonder if it will allow me to not specify the any on there. Indeed it will. Okay, so this is sufficient for it to figure it out. X rocket 5. So after the carets, we need to put a function or a partial function. Wasn't that? Oh. Caret S rocket. Let's do this one as a partial function. Case string. S is a string. I want to see if this will work with a full function. S rocket S dot to double. And I'll put the or down here on the next line. And I have an extra close parentheses, which makes it very unhappy. Okay. In the case of the floating point number, this is actually what I want. I want this to be a function that takes whatever string was output by this, and in fact you can see when I hover over, S is inferred to be a string because that is the return type for the parser for the floating point number. And in fact, if we hover over this, you can see that it's a parser of string. Okay, but I've kind of hard-coded the rest of these in a way that's a little bit silly. If we do this, okay, this is kind of the next easiest one. The floating point number was the easiest. This would be the next easiest. One way of dealing with this would be so I'm going to define a partial function here. And we're going to have a case, and the case I'm going to use a pattern. Tilde F tilde Okay. So note that I'm kind of stripping off the parentheses, I match this as a pattern that has string, tilde, f, tilde, and a string, and the f is the only part that I care about. That's what this matched, and since the form D gives us parses to a double, that happens to be a double, and we can return it here. We can simplify this a bit by using a slightly different form of the tilde, where, and in fact you can tell it started giving us some errors. When you put an arrow on the tilde, what that says is that you only care about the stuff the arrow points to. So in this case, I don't care about the parentheses. I didn't need them for what I was doing. I only cared about what was matched in the middle, and so I can have this simpler case, which probably expresses very nicely as x rocket x, and indeed there we go. Okay, so the factor D is actually now written. It's perfectly happy. These other two are going to be a bit more complex. So what do these give us back? We kind of saw that we could make a case with a pattern for this. So what we can do here is, I'm going to use the case notation. In fact, I'll put it down on the next line so that it's easier to work with. So this is going to return a T1 followed by a list, and this is a list of well, LST, rocket, we'll put our 5 there again. The type of LST is a list of tilde of string and double. Okay, and that's because the first thing that was matched here was a string, and the second thing was a double. So we start off with our first value here, and then we need to run through our list and apply a function to this. We can do this in lots of different ways. Probably if we do a fold left across the list, and we're going to, oops, sorry, this is LST dot fold left. The initial value is T1, and the function that we pass into here takes the accumulator, our number, we'll just call it x, and then it takes our tilde, or the tilde tuple. And we're supposed to return, now if I made it just return x, this would wind up giving us back T1 in the end. It is going to be x, but then it either needs to be plus or minus the value of the next thing. And so how about, yeah, because I need to change my operators. So if t dot underscore 1, so the thing to note here is that to pull out the two elements of the tilde, we use an underscore 1 and underscore 2 just like you would for a tuple. And so if that equals plus, then I want this to return T1 plus T, else T1 minus. Yep, and this should be T dot underscore 2 dot underscore 2. Okay, so let's go back over this and kind of see what's happening. The fold left, remember, runs through a list one element at a time, and starts with, you have an accumulator here, so the value of the first thing that was matched, the first term D, is the beginning value for our accumulator. Turns out if there's nothing there, we'll just get back that accumulator, and if the list was empty, which is the behavior that we want, if the list is not empty, it's going to call this function for every element of the list. So the accumulator is passed in as x, the arguments of the values of the list are passed in as the t, which are our tuple values, and if the first element of the tuple is a plus, we're going to do addition, and if it's a minus, if it's, in this case, if it's not a plus, we happen to know the only thing it can possibly match is a plus or a minus there. Well, since I have that code, it just so happens that the next case looks remarkably like that. And just to make the names make a little bit more sense. I'm going to change the T, since it's not term 1, to F. And if it is a star, then we do multiplication, else we do division. So now we should be able to do a call like what we did before, but I'm going to use the form D parser for this. And this should give me 5 times 5 is 25. It's the last printout. Oh, I don't have a print line in there. But you can see there's a 25.0. Just to make sure it's working, we'll get rid of the parentheses and we get a 17. What if we make this an 8 over 2? Then we should get 2 plus, and then this quantity happens first. It should be 3 times 8, which is 24. Divided by 2 would be 12, and so we should get 14. And so if we run this, yes, we'll save. 3.5, not the value I was expecting. Not even certain how we would get that value out of there. 3.5 would be 7 over 2. Is there any way that I can combine these in such a way that I would get 7? Or 1.5 would be 3 over 2, which could happen technically if we lost the 8 over. And I could see that happening if somehow I lost something in this fold. If that's what's happening, this should give me 6 because it's passing over the 8. Or sorry, 6 there plus the 2 gives me 8. Times 4, if it skips over all of these, I have a 3 times 4 would be 12 and 14. Indeed, that does appear to be the bug. Okay, so what am I doing wrong in my folds? Well, when in doubt, put in some print statements. Print line x comma t. Need some curly braces so that this doesn't get unhappy with me because we have multiple lines in there now. And what is that? Oh, the curly brace needs to go there. Okay, so that everything matches up appropriately. And now when we run this, we get the first time it passes the 3 and it says times an 8, and then that goes and it passes it to a 24 which says times and 2. Okay. Now that's interesting that a 24 times 2 somehow gave me 6. Oh, I know why. Because I didn't do x times. Those should be x's there, and these should be x's here. I'm supposed to pass through the accumulator. Now we'll run. Okay, and 194, which probably seems right given that I put a whole bunch of multiplication in there, and indeed things are accumulating up nicely. Let's take out this extra print statement for the debugging, and the curly brace there. And get rid of those. Okay, so once again, this should be 24 divided by 2 would be 12, plus 2 is 14, and sure enough we get 14. Okay, so there we go. That was we now have a parser that uses the combinator parser, or the parser combinator, and we are able to parse 2 double values. The advantage of this over the recursive method that we wrote a few chapters ago is that this is far more flexible as far as the grammars go. If I can come up with, if there's a new rule I want to add to my grammar, I can do that quite simply here. What we'll do in the next video, and the last one in this chapter, is we will take this one step further, and instead of going straight to doubles, I will produce a parse tree, and that's when the class up here, and you might have wondered why I made this a class originally, because I want this to include a parse tree of whatever formula so that it can be quickly evaluated, and we'll talk about how we could get a variable in there as well. But that's it for this video, and we'll come back and look at that next time.